Okay, welcome everyone to this Friday seminar. And Francesco could not join us, so I will introduce the speaker. So my name is Ilya Sinaisky, and I'm at the University of KwaZulu-Natal. And today's speaker is Dr. Martin Weigt, and he will talk about applications of topological algebras to the quantum computing and information. Martin is a rated NRF researcher, and his research is primarily focused in the area of mathematical physics and the operator theory. But as we're going to learn, he's working on application of those interesting mathematical and non-trivial mathematical concepts towards the quantum computing and theory of quantum information. Take it, Martin.
Okay. Thank you very, very much for allowing me to give this presentation this afternoon as part of the seminar. I just want to mention that, okay, I've got a new device at the moment, and I've got trouble with turning on the camera when it comes to Zoom. But on Microsoft Teams, I don't have an issue with that. Okay, so apologies if you cannot see me at all. Okay, what I'm going to talk about this afternoon is mainly some applications of topological and unbounded operator algebras to quantum computing, which maybe might not be that well known. Also, my main area of research is in topological algebras, unbounded operators, operator algebras, and then also with applications to mathematical physics. So the aim of this talk also is to give an introduction to the world of the unbounded operator algebras, that at the same time. So, okay, so I assume in this talk no familiarity with unbounded operators at all. So I will start from the beginning. Okay, I think right, I will start by just introducing the von Neumann formalism of quantum mechanics. So those are observables such as position, momentum. They are represented as self-adjoint unbounded linear operators on a Hilbert space. And then the states of a quantum system are represented by vectors in the Hilbert space having norm 1. And the measurement of an observable are the eigenvalues of the self-adjoint unbounded operator corresponding to the observable. So of course, if it's self-adjoint, then the eigenvalues are real, and of course we want to take real measurements. So this does make sense. And then if you're looking at a time reversible quantum system, then the dynamics of that system is actually going to be just the usual thing coming from the Heisenberg Schrödinger mechanics. So A to this, so you've got the A there in the middle, and then you've got e to the ith and e to the minus ith on the left. And then the state goes from phi of phi actually to u of t of phi, where u of t then is the unitary operator e to the ith, with h being the Hamiltonian of the system, assumed self-adjoint. Okay, that is the usual von Neumann formalism in quantum mechanics when you try to make all of it rigorous. But now what one can also do is to generally move over to locally convex star algebras and observables of a quantum system. And that is actually because most our observables, such as position and momentum, are actually mostly unbounded operators on a Hilbert space. And then the only question is now, how do you work with unbounded operators? If you can bring in some algebraic structure, that would actually help a lot. So that's why we introduce the locally convex star algebras, which I'm also going to introduce shortly. One can then represent observables as self-adjoint elements of a locally convex star algebra with identity. I'll mention shortly what that is. And then the states of the quantum system, those are the positive linear functionals, which maps the identity element of the algebra to the scalar 1. And the dynamics of the time reversible system is represented by a one-parameter group of star automorphisms of A. That's if it's time reversible. And if the dynamics of the system is time irreversible generally, then the dynamics is not described by a one-parameter group of automorphisms, but by a one-parameter semigroup of completely positive linear mappings from the locally convex star algebra A to itself. And I will also introduce those concepts as time goes. A locally convex algebra is actually again a star algebra, but which is not necessarily a C-star algebra or a Banach algebra. That I will now introduce. So then this is just how we can generally take the dynamics or represent our quantum system if we work generally with unbounded operators. So then they cannot be elements of a C-star algebra. So we need the locally convex structure for that. Okay, so to introduce that, I first have to say what a topological algebra is. That's an algebra which is a Hausdorff topological vector space in which multiplication is separately continuous. And so not necessarily jointly. A topological star algebra will be a topological algebra equipped with a continuous involution. So if you wonder what an involution is, you can think of the involution of bounded operators on a Hilbert space, like we do in B of H. And then it's actually a generalization of that concept. In a C-star algebra or Banach star algebra, we also have an involution there. And then we define the involution here in the same way, having the exact same properties. And then finally now a locally convex star algebra, that will be a topological algebra, topological star algebra. So in other words, having continuous involution, which is also a locally convex space at the same time. In other words, so we remember that it's a topological star algebra. So that's a topological algebra. So it's also a topological vector space. But the topological vector space part is specifically a locally convex space. So we have here addition, scalar multiplication, and an algebra, in other words, a multiplicative structure, and also an involution. That's what we have in a topological algebra. So all Banach algebras and C-star algebras are topological algebras. All C-star algebras are topological star algebras, but now they need not be normed, which will help us when we work with unbounded operators. So I'm first going to introduce all the mathematical background that we need in our setting. Okay, what's a positive linear functional, which I've alluded to earlier? So if you work in a star algebra, so that's only a structure, a set with addition, scalar multiplication and an involution. Then a positive linear functional on A is a linear functional on A such that it maps all elements of the form x star x to something, to a non-negative scalar. So a non-negative real number. And this is exactly the same as the definition of a positive linear functional in a C-star algebra. And then a state on a star algebra with identity element 1a. It's again a positive linear functional phi on A with the identity equal to 1. And the states are actually the important classes of positive linear functionals we work with. because again, that actually generalizes the concept of probability measure. So if you want to find the probability of a particle in a certain interval, that would have to be between 0 and 1. So it's like we normalize and we say phi must map the identity to 1. So that's where this comes from. And that's what's important in quantum mechanics and applications. For quantum mechanical purposes, a state is represented by a trace class operator. What I mean by that, so that's a special type of bounded operator. So in other words, phi of x would be the trace, the ordinary trace of tx as an operator. And that's for all x in a star algebra consisting of unbounded linear operators. And then t is automatically bounded by definition. Okay, one thing I can mention here is that there is already quite a lot which is known about star algebras which consist of unbounded linear operators. So there one can know how to add, take scalar multiplication, and then take multiplication of unbounded linear operators so that they form a star algebra, but also one can equip them with some nice topologies. So that these things turn out to be generalizations of C star and von Neumann algebras. Automatically note that if you represent phi already as the trace of tx, where t is a trace class operator, then already that makes the functional ultra-weakly continuous, or what you call a normal state. But that's what's important for our purposes. So we will work with that. Okay, one class of unbounded operator algebras which I now will introduce and which will set the scene in our work are those called generalized B star algebras or GB star algebras. Those are actually direct generalizations of C star algebras that were first introduced by Professor Graham Allen in the late 1960s, and then taken further by Professor Graham Dixon in the early 70s. Okay, so now I shall give the definition. And I will explain how, as the talk progresses, why these things matter. And also recently, myself and 3 of my colleagues, that's Maria Fragolopoulou, Atsushi Inoue, and Ioannis Zarakas, we recently published a book on this as the lecture note series in mathematics, Springer. Okay, so we start off with a locally convex algebra, which is pseudo-complete. Pseudo-complete is you can just think of as a weaker form of completeness. It's not quite complete, but it's a weaker form of it. And it's so locally convex, pseudo-complete topological algebra having an identity. And then we say that A tau is a generalized B star algebra, or we just call it GB star for short, if A has a star subalgebra, AB0, containing the identity and satisfying the following conditions. So the star subalgebra is again a subalgebra of A, but closed under the involution star. Okay, first, AB0 is a C star algebra with respect to the norm. With respect to some norm, which is usually the Minkowski functional coming from that algebra. Secondly, 1 plus x star x, the inverse thereof, always exists. And not only does do these inverses exist in A, but specifically in the underlying C star algebra, no matter what element x in A you take. So that inverse will always be a bounded operator and be an AB0, the C star algebra. And then the closed unit ball of AB0 must necessarily be a bounded subset of A, and that's bounded with respect to the topology tau on A. So it's tau bounded. Okay, lastly, there's a proposition by Butt that if A is a GB star algebra, then necessarily AB0 is actually dense in A with respect to the given topology tau. So it's a dense subset. One can think of, therefore, as a GB star algebra as taking a C star algebra, and you are just making it bigger by chucking in, if I can call it that, unbounded elements, which these elements are actually that you are throwing in to make it bigger, actually turn out to be unbounded operators on a Hilbert space. And I will say something about that shortly. That's how you can think of it in a nutshell. And we especially consider it would be nice if our algebra of unbounded operators has some things in common with C star algebras, as those are the things that we actually need. And those are things like states and representations being the most important, especially in the quantum world. So that's all what we need to know about a GB star algebra. Think of it as an enlargement of a C star algebra, and then also that which is dense and which has the inverses of 1 plus x star x. What are some examples, you might ask? So on this slide and the next slide, I give examples. So if you take any complete locally convex star algebra, where the topology is defined by a directed family of C star seminorms, then that is what we call a pro-C star algebra. Those are examples. If you look at C of x with a topology of uniform convergence on equicontinuous subsets of x, that's a pro-C star algebra when x is a completely regular Hausdorff space. Also, one nice example is when you take the algebra by Arons, the intersection of LP spaces, and you take the intersection over all p bigger equal to 1 over 0, 1. This turns out to be what we call a Frechet GB star algebra, and it's not a pro-C star algebra. In other words, the topology is not defined by a family of C star seminorms. By Frechet, I mean complete and metrizable. So it's defined by a metric. The topology is defined by a metric, and it's also complete. So all Cauchy sequences converge. And then every unital closed star subalgebra of a GB star algebra is GB star, like we have in a C star algebra. And then also the various star algebras of measurable operators affiliated with the von Neumann algebra, those are also GB star algebras. Although now in those topologies, which generalize the topology of convergence in measure, need not be locally convex. But they are GB star in the more general sense of Dixon, who actually then just took that definition of GB star algebra further by not necessarily insisting that the algebra be locally convex, but just a topological algebra in general. But in some cases, there are instances where the topology of convergence in measure is locally convex, and the underlying and the algebra need not coincide with the affiliated von Neumann algebra, so that it's still strictly larger than the von Neumann algebra. And these are also algebras which are very often studied nowadays. And lastly, GB star algebras for which the underlying C star algebra is a W star algebra or a von Neumann algebra, concretely that is, they are actually connected with extended W star algebras and also the unbounded Hilbert algebras. So they actually do occur in various guises out there. We might maybe just not recognize them as such. The last two slides. Okay. For the preliminaries, a pure state on a GB star algebra is like a pure state in a C star algebra. So it's if for any positive linear functional psi with psi less than equal to phi, then you can get some lambda between 0 and 1, so that C is in fact lambda times that phi. So phi over here is the pure state. And then you can take any other positive linear functional and write it as a fraction, you can say, of the pure state. So that's like in a C-star algebra. Every C-star algebra has an abundance of pure states, but now there are GB-star algebras which do not have pure states. So that's this example which I mentioned earlier, which is the intersection of all the LP spaces. In fact, it has no characters, so therefore no pure states. So not everything about a C-star algebra necessarily does carry over to a GB-star algebra. The last slide on this, in a C-star algebra, you can represent that concretely as a star algebra of bounded operators on a Hilbert space. Now, a GB-star algebra, one can do the same and generalize this idea, except that now you represent it faithfully as a star algebra subalgebra in this L plus of D. And this L plus of D is actually the set of all unbounded linear operators, which maps the domain to itself, and for which the adjoint also maps the domain to itself, and they are closable. So it's those type of unbounded linear operators. And then the faithful star representation is just a star homomorphism into that. So that therefore you represent A as some kind of a star algebra of unbounded linear operators on some domain. And this domain, of course, is dense inside a Hilbert space. So the unbounded operators are not necessarily everywhere defined. They map the domain to itself, and the adjoint maps the domain to itself. And that's why I mentioned earlier that you can think of a GB-star algebra as just taking a C-star algebra, and you make it bigger by just throwing in unbounded operators. One should keep in mind that unbounded operators are not easy to work with compared to bounded operators. And so this is why it's good to bring in some algebraic structure so that we can try and get something going which maybe has some traits in common with the C-star algebra, the more familiar territory. Okay, hopefully this will give a bit of a feel for what these GB-star algebras are. Okay, next two slides, I just want to remember some very basic fundamentals of quantum computing. So I've just taken it down in a nutshell, really. So in a digital computer, we store bits either as zeros or ones. But in a quantum computer, you take the basic bit of information as a superposition of 0 and 1s. That is, you can think of a state, let's say, as some kind of a linear combination of phi1 and phi2, where the t runs between 0 and 1. And you can think of phi1 and phi2 as pure states, say. So that's a superposition. One example, let's just say phi1 can be the ground state of the hydrogen atom representing 0, and then phi2 can be the next excited state of the hydrogen atom representing 1. And then maybe, okay, one can maybe even go as bold as to say one can think of any quantum system as a quantum computer and vice versa. All right, so a quantum computer done by a computation which is done by a quantum computer can be translated into the time dynamics of the system that it simulates. And then if you especially are working with reversible systems, then a circuit in a quantum computer can be made up of gates which are described by unitary matrices. So you translate, so then understanding unitary dynamics, then translates into doing some computation on a quantum computer. This reference number 9 comes from our list of references, which I'll show you toward the end. In certain crypto systems, we are all probably familiar, such as the hardness of factorizing large numbers into prime numbers. Or let's say elliptic curve cryptography, they are basically under threat by quantum computers. So the hunt is also on to find algorithms which cannot be solved easily in polynomial time by quantum computers. So for obvious reasons. So, okay. So that's just some of the fundamental basics. I just want to say something about quantum channels. And this also brings me now into operator space theory. Some of you at least might be familiar with operator spaces, which is a mathematical tool used in quantum information and computing. So by an operator space, I mean that you start with a Hilbert space, and then you take any closed subspace of B of H, which contains the identity operator of B of H. So that when I mean operator space, I don't necessarily mean that it's closed under multiplication, but only addition, scalar multiplication, making it a vector space, and then being norm closed with respect to the operator norm in B of H and containing the identity. Hence, I use the word space and not algebra. So if you now take a mapping between two self-adjoint operator spaces, by self-adjoint, I mean that it be closed under involution, the operator involution, or the operator adjoint on B of H. We will say that it is completely positive if this mapping, taking you from the n by n matrices over S1 into the n by n matrices over S2, is a positive linear map for no matter what size matrices you take. How is this Tn defined? You take what Tn does to this matrix Xij, so that is now entry in the ith row, the jth column, Xij. It just says, okay, now replace the entry in row I and row j with T applied to Xij, with T applied to the entry in the ith row and the jth column of that matrix. So you just apply T to each entry. If that mapping is always a positive linear mapping, that means taking positive operators to positive operators, no matter what the n, no matter what size matrices we are working with, then we say it is completely positive. In quantum information theory, quantum channels are used to represent transformations of quantum states. So what do I mean? A quantum channel is a trace-preserving, completely positive linear map between the operator spaces, which maps density matrices then to density matrices. So recall for our purposes that quantum states will be represented by density operators, as I mentioned a few slides back. So in other words, by trace class operators, and these are necessarily bounded linear operators. Of course, that makes the functionals automatically normal or ultra-weakly continuous. Now I'm going to start tying in the topological algebras with the operator spaces. From what I understand, it is still the operator spaces are very much in use in modeling systems in quantum information, but I can also show basically how one can take operator space theory and then just also chuck in some additional techniques using unbounded operators. So that's what I will show you now in the next few slides. First, taking just quantum channels further. Let us suppose now we take our quantum system to be a locally convex star algebra. So we take as its self-adjoint elements the observables of the system. So the spectrum is real, and that can be represented, and we assume it is represented as a star algebra of unbounded operators on some Hilbert space. So in other words, like, for example, the GB star algebra, which I showed you further, that can be represented as a star algebra of unbounded operators on Hilbert space. And then we assume that the quantum states of the system correspond to states of the star algebra of unbounded operators. So that would be, we'd say f of x would then be the trace t of x for all x in B. Notice what B is. B is the star algebra of unbounded operators, which is represented by that locally convex algebra. And where T is some density operator. So we make that assumption. Now there is one thing that T need not actually belong to this star algebra of unbounded linear operators, but it's generally in B of H. So in other words, if you take your unbounded linear operators, it's defined on some domain, and now you take the norm closure of that domain, you get a Hilbert space, and it's this Hilbert space that we are working with. So generally T floats around in B of H. It need not be in B. So then if one wants to know how the state F1 of B transforms to another state F2 of B, then one must apply the quantum channel to the operator T1 corresponding to F1, say, to see what the density operator of F2 will be. That's what it will have to be. So in other words, F1 and F2 are states, let's say, on the star algebra A or equivalently B, but the density operators need not belong to B. So then you have to apply the quantum channel to see how the density operators transform, so that we can then try to get an idea how the functionals or the positive linear functionals themselves transform. Okay, I'll show one illustration of this. Okay, so now we are going back to GB star algebras. These things, they have states which separate the points. So in a GB star algebra, one also has an abundance of states, and you can form the GNS construction and then the faithful representation via Dixon. Okay, so we assume it is faithfully represented as an unbounded operator algebra M, which we know can happen. Take a state on A, which is identified with the state F on M. So in other words, M is the unbounded operator algebra, and it is actually, let's say, it is represented by this infinite series of WXCN. In other words, what I actually mean is that f of x is actually an infinite series of these inner products. And then this you can actually also write, express in terms of a density operator, in terms of the trace. And that symbol here means that the overline means the closure. And then T over there is the corresponding density operator, which corresponds to F. All right, at this stage, I'd like to also say that if you represent a functional in this form, that's equivalent to saying that the functional is ultra-weakly continuous or normal. So then now we know exactly that these are precisely the functionals or the states we should be working with. All right, now what one can say is let phi of t be a semi-group of completely positive linear mappings of this unbounded operator algebra M. This could represent the dynamics of a time irreversible system. Should the system be time reversible, then the completely positive linear mappings will turn out to be star automorphisms. So these are star automorphisms are completely positive. So here we are trying here to cater for the most general situation which can occur. Also, for simplicity, let us suppose here that our state, our semigroup of completely positive linear mappings are of this form, V of t star x, V of t, and all the V of t are isometries on the underlying Hilbert space M. These are actually the simplest types of completely positive linear mappings, and they do also occur in quantum applications quite frequently. And then one can actually say that if you now apply the state f, which we have in the previous bullet, and now you apply it to phi of tx, phi of t being the completely positive map. So this phi of tx, let's say, is telling us how the observable x transforms under phi of t under a certain time. So you take an observable, and then t units of time later, the observable has transformed to phi of tx under the completely positive map. Then one can go and write this again as this type of series where t over here is now the underlying corresponding density operator. And now one can actually show that if you now take, let's say, an operator space which contains the density operator t in the first bullet, and then let's say you look at the and then you look at an operator space which contains this this operator as a density operator, and then you consider the mapping going from the one operator space to the next, which we define as this. So the mapping which maps you from this density operator to the next density operator under the transformation. So that's now t seconds or t units later under this time dynamics. Then this again can be shown. This can actually be shown to be a completely positive linear mapping. But due to interests of time, I don't necessarily have time to show you how this works out. But it's not very difficult to show that. Okay, so in other words, this actually turns out to be a quantum channel. So one can actually therefore add to the existing mathematical techniques of operator spaces using the unbounded operator algebras. One can then add to that to actually do calculations and computations involving quantum information and quantum computing. So maybe that can make certain other things possible. As a second illustration, when solving the time-dependent Schrödinger equation, one generally finds it can be very, very difficult to even to solve that equation in some cases. So that's now especially the time-independent one. So that can be a lengthy process even for the hydrogen atom. So for quantum purposes, one is really interested in the time evolution of a state, as this is equivalent to performing some computation. Very often that happens. So let us suppose now we are working with a reversible system. Then the time dynamics of that system is given by a group of star automorphisms. So if we suppose it's reversible. And then the initial state, x, then will actually transform to this state. It will transform as follows after t time units. So in a quantum computation, one usually knows the starting or initial value, and then making it easier to determine how the initial state evolves. So that could make it easier then for solving the Schrödinger equation. And then e to the ith, where h is the Hamiltonian, that can actually also not be as easy to compute as one generally thinks. But hopefully it's easier than the original problem of solving the Schrödinger equation directly. And again, one can do all this when you work with a star algebra of unbounded operators or locally convex algebra. Also, one important feature in quantum computing is entanglement. In quantum information, the quantum entanglement serves to be an important property for the following. If one state in a system gets lost, then one can retrieve the information from the other system if the states are entangled, or just hope that one can do that. Whereas if the states are independent and one of the bits gets destroyed or damaged, then that information will be lost if they're not entangled or independent. Also, there are one can have a quantum internet service, and I think in China this is already operational in at least one city. One can securely share information by two users sending information via states to a central processor. That processor can then entangle the states and then send them back to the original user. And then quantum entanglement will also make it impossible to copy or alter information. Okay, so the question is, how do we handle quantum entanglement in our mathematical setup? So for that, we require tensor products of GB star algebras. And this is actually work that was carried out by myself and Maria Fragolopoulou and Atsushi Inoue back in 2009. So that now we've published a paper on this, and this also appears in our book. So you start with two GB star algebras, and then you can represent the completion of the tensor product with respect to the locally convex topology on the algebraic tensor product, making the multiplication now not only separately continuous, but jointly continuous. Under certain conditions, one can make this a GB star algebra. And we will always assume that those conditions are met. Then a C star algebra will be said to be a nuclear GB star algebra if the underlying C star algebra AB0 is a nuclear C star algebra. And then I make an assumption from here on. We will always assume that the locally convex algebra tau on the algebraic tensor product of the two GB star algebras makes the multiplication jointly continuous. Otherwise, when you take the completion, you don't necessarily get an algebra. So that's to make sure you get an algebra, a topological star algebra. And then under certain conditions, you will then get a GB star algebra. Why are tensor products useful? Because we need to go over to joint systems. So let's make an assumption, and let's just say you've got two quantum systems, Q1, Q2, which are where the elements are taken to be inside those two GB star algebras, A1 and A2 respectively. Then one can represent the observables in the joints. In the joint system of Q1 and Q2, the joint system, as self-adjoint elements as some kind of complete tensor product, GB star algebra. And that's then with respect to some topology on the completion. So now we are actually doing things on a more abstractly, from a more abstract algebra point of view. In order to get a unique complete tensor product of A1 and A2, then one usually chooses the algebras to be what are called linearly nuclear GB star algebras of the two quantum systems. Okay, so one would usually only want to have one way in which to form the quantum system, and not have to have more than one way to do it, But also these linearly nuclear algebras are what's actually suitable for quantum physical purposes. And that's what I will show you. So now our joint system, therefore, is actually this complete tensor product GB star algebra. Okay, just a little more. Oh, and one example, any inverse limit of finite dimensional C star algebras will be a linearly linearly nuclear pro C star algebra, which is not a C star algebra, and therefore linearly nuclear GB star algebra. One can also say to take a quantum system to be one which is linearly nuclear is actually a correct choice in light of the following. Any Frechet linearly nuclear GP star algebra is faithfully represented as an O star algebra of unbounded operators on some Richt-Hilbert space. So a Richt-Hilbert space is where you take an enlargement of the Hilbert space to include other, I should maybe say, states. Because very often when you solve the Schrödinger equation, for example, like the infinite square well, you sometimes get solutions which are not square integrable, so they do not belong to the Hilbert space, so they belong to something beyond the Hilbert space in what is called a Richt-Hilbert space. And again, a linearly nuclear GB star algebra you can represent this way. Also, if you take a GB star algebra which is linearly nuclear, then it will have an abundance of pure states. Earlier on, I mentioned that there's an example of a GB star algebra having no pure states. So if we make it linearly nuclear, then we are fine. Okay, so then we can make it, then we've got actually an abundance, which is what we would like. This result actually goes back to Bochus, Ingvarsson, and Hegerfeld. So you take a linearly nuclear, locally convex star algebra. By linearly nuclear, then I just mean nuclear as a locally convex space. Then for any state phi on A, which makes this map over here continuous, then you can actually get a set, call it Z, and a weakly measurable map to the extremal or pure states of A, and a measure mu on that set, having measure 1, so that you can actually write that state as an integral of pure states in a nutshell. So you have an abundance of pure states from which then you can manufacture all the continuous states making for which that map X goes to phi of X star X is continuous. So you can then manufacture all of them. So that especially works if it's linearly nuclear. That means nuclear as a locally convex space. It need not be nuclear GB star algebra, but nuclear as a locally convex space. Also, one can generalize that result to any linearly nuclear metrizable, what we call locally convex quasi-star algebra. A quasi-star algebra is again a collection of unbounded operators, which is a vector space, but it's actually a module over some algebra, call it A0. So you can't necessarily multiply, but you can only multiply an element in the quasi-star algebra with an element inside the actual algebra A0. And it has an advantage, especially when working with unbounded operators, because multiplication of unbounded operators is not a trivial affair, as we all know. Then again, if you take one like this, which is metrizable and linearly nuclear, then it again has a decomposition. A state will have a decomposition into pure states. So one can generalize it to the quasi-star setup. These results I'm mentioning here have been published in one of my publications, which I will show you at the end of the talk. Okay, so so that's what I'm showing you here. Also, one of the reason why the quasi-star algebras are important, because one can break the region up into smaller region, consider the dynamics over the smaller regions because that might be easier. And then you've got to unravel the dynamics of the overall regions by actually gluing the dynamics of all the individual regions together. But now in an algebra, this gluing together process might not work. So in other words, you do not necessarily have what are called the thermodynamical limits. So you need a quasi-star algebra to contain the dynamical limits, so that when you glue together the dynamics of the individual regions, which are easy to handle, then you're getting the dynamics of the overall region. And a quasi-star algebra is more suitable. But we will restrict attention first. We restrict primarily attention to the algebras, the GB-star algebras, just for sake of simplicity, to see just to get a general idea how it works. And then they can also serve as appropriate, then linearly nuclear metrizable, locally convex quasi-star algebras can therefore also serve as appropriate models of quantum computers. In light of these two results, especially the first theorem. So again, the quasi-star algebras, they are very intricately connected to unbounded operators, and one usually represents these things as some kind of a module over a C-star algebra, let's say, consisting of unbounded operators. Just want to remind again what a star representation is. So that is now, if you take a locally convex star algebra, an unbounded star representation will be a star homomorphism from A to L dagger D. And this will be now important in mentioning how we can handle quantum entanglement. Every star representation going from A to L dagger D gives rise to a positive linear functional for all x in A, where C is in D. So this is like the GNS construction in the C-star algebra. One can do the same there. Okay, 2 slides where I will just mention just remind how we handle quantum entanglement in von Neumann's formalism. In von Neumann's formalism of quantum mechanics, we associate Hilbert spaces H1 and H2 with the states of 2 quantum systems respectively. So that means vectors having norm 1. And then to consider the joint system of Q1 and Q2, one looks at the Hilbert space tensor product associated with the states of the 2 quantum systems. So that would then be the state system of our joint system of Q1 and Q2. And then a separable state for the joint system will be an elementary tensor of 2 states. So C1 coming from H1 and C2 coming from H2. And then an entangled state for the joint system of Q1 and Q2 is any state which is not separable. So not expressible as an elementary tensor. Now, the reason I mentioned this is because now this makes it possible to see how one can actually bring quantum entanglement into the GB star setup. So the one is actually, if you take let's say we take 2 linearly nuclear GB star algebras, and we assume now that our joint system, or we take a tensor product GB star algebra, we assume that this is a GB star algebra under some topology. And now you take a state on this tensor product. Then there is a representation of A into L dagger D Okay, so that what phi does to a finite sum of these elementary tensors will be precisely that. And then we will say that a state will be separable if the star representation above can be chosen to be elementary tensor. So if that state C over there in the first bullet, in the last line, can be chosen to be an elementary tensor under some representation, we'll call it a separable state. So in other words, we try to mimic the von Neumann formalism. And then it will be entangled if phi above is not a separable state. So if you cannot represent it in such a way that the C over here is an elementary tensor. The only problem with this definition is that now it depends on how we represent our tensor product GB star algebra as unbounded operators on some Hilbert space. It depends on what the star representation is. So we remember that the L dagger D contains unbounded operators. So maybe something more suitable is the following. The second definition. Again, we assume that we start with two GB star algebras that can be linearly nuclear. And you again assume that the tensor product is GB star under some topology. Then one can define a state to be separable if it's an elementary tensor of two states, the phi1 on A1 and the phi2 on A2. And then an entangled state can be one which is not separable in the above sense. The second definition can be shown to be made equivalent to the first definition, but I don't think that the first definition implies the second definition. Okay, I will end this talk just by giving some results. Okay, just on how we can actually achieve an entangled state. But I don't have time to give you any proofs of that. So if you now take two GB star algebras, you'd look at their tensor product under some topology. And now what we will do is we will suppose that the underlying C star algebra of this GB star algebra is just the tensor product of the C star tensor product of the underlying C star algebras of those two algebras. So that can be under min or max. It will not make a difference because let's say we take minimum. Then any pure state, and I repeat, any pure state on A, you can then decompose as a tensor of two pure states on A1 and A1 and A2. So phi1 being a tensor of A1 and a pure state on A1, and phi2 being a tensor of A2. Now that's assuming, of course, that A has a pure state. And we're assuming here that at least one of A1 or A2 is commutative, at least one. We can now also look at the converse of this theorem, namely, again, a Frechet GB star algebra, meaning complete metrizable, and both having at least one irreducible representation. And again, we suppose that the tensor product is a GB star algebra under some topology, and where the underlying C star algebra of this complete tensor product GB star is again the C star tensor product of the underlying C star algebras there and there. If we were to know that every pure state on this tensor product, call it phi, is decomposable as an elementary tensor on the two underlying GB star algebras A1, A2, and if both of A1 or A2 have at least irreducible representation separating the points, then at least one of A1 or A2 is commutative. So therefore, if you want a quantum entangled state, you would have to start with two non-commutative Frechet GB star algebras. That's exactly what we have in quantum physics in any case, non-commutativity. So one can say if A1 and A2 are two quantum systems, and they are both representable, let's say, by non-commutative Frechet GB star algebras having sufficiently many irreducible representations to separate the points, then that GB star tensor product will have at least one entangled pure states in the sense of the second definition. So that will be useful in that sense. Okay, now I'm just about the references. I've given here a number of references. The references which are highlighted in green are references are texts which have about topological algebras and unbounded operators. In case you would like to know more about the theory of topological algebras and unbounded operators. So the references in green should definitely give you a lot to go on. And also this reference 7 over here is the recent book which was published by myself with Maria Fragolopoulou and Atsushi Inoue and Ioannis Zarakas. And that's lecture notes in mathematics. And then, yeah, just some more references on unbounded operator algebras and topological algebras. Many, but not all of the results which are presented here appear as reference number 14 in this, but not all the results, some of the results which I've presented. And then, okay, lastly, okay, just the book flyer in case you want to just see what it looks like. Okay, and this brings me to the end of the talk. Thank you very, very much for your attention. Are there any questions or comments?
Thank you very much. Yes, the question is, if anybody have a questions, please just unmute yourself and ask your question because we are in the meeting setting. So you can just unmute yourself. And maybe while people are thinking, I can ask a question. So you create a construction to define the entanglement. And because, kind of like what I can gather from your talk, you're kind of in the very, very beginning of application of this operator algebra formalism to the quantum computing and quantum information tasks. But how you would define the measure of entanglement? And can you also incorporate the locality concepts which any entanglement measure should satisfy?
Okay, that's a good question. That's actually concerning your first question, the degree of entanglement. That is something I have not thought about yet, but much of the work I'm doing is actually ongoing. So that's actually something I also want to think about. Concerning your second question on locality, I've recently published something on local nets of unbounded operators in which I brought in something about locality. So that's where regions are separated in space-time. So that's something in a separate publication. But and that brings in local nets of unbounded operators. So technically, there you would say, for example, that in the bounded operators case, that the operators actually commute. But okay, yeah, that's something else again.
Okay. And kind of like, of course, all this formalism have probably the direct application to the continuous variable quantum computing because with the standard qubits, everything is bounded and everything is finite. And all of this mathematics is reduced to the epsilon complicated linear algebra, I assume.
Yes. Especially, let's say, if you are transforming from one state to another, then sometimes that can happen continuously. So yeah, so then one can see how to bring all that in.
Okay. I do not see any questions from the audience. So the talk is recorded and it will be uploaded to the NITEX YouTube channel within a few days. Thank you very much, Martin. And
Thank you.
hopefully, yes, we can hear the continuation of the story, because really, it's really you're in the very, very beginning of application this to the quantum computing. And I mean, formally speaking, it's still, from my assessment, it's not even quantum computing, it's a more quantum information theory. So
Yes.
to make it quantum computable, quite a few more steps needs to be done.
Yes, exactly. But yeah, so I hope I've given some indication as to how these things can actually be used.
Yes, thank you. Thank you.
Okay,
Okay,
thank you. Thank you very, very much.
thank you very much. Thank you. Bye-bye.
Thank you. Bye-bye.